Hello. So today I'd like to talk about consciousness. The topic of consciousness appears in the context of AI quite often, but a lot of times people don't think there's any relationship between consciousness and intelligence. And even some people kind of shy away from talking about consciousness because it's a very elusive concept. So, but as a company, which I founded in 2013, we do some research into consciousness, and we are even trying to build artificial consciousness through AI research. But the purpose is not necessarily to create artificial general intelligence. We want to understand what consciousness is by trying to implement it. So, so my background is in neuroscience, and I studied how the brain generates consciousness using neuroimaging techniques. But a lot of times, the concepts available in cognitive science or neuroscience are not very satisfying because they're not well defined. But once we start thinking about how to implement those things, we have to be really specific, and we even have to define it. And so, and also, there hasn't been, well, of course, there has been some research into constructing consciousness, but because now, because of the strong interest in research into artificial intelligence these days, we can borrow a lot of new ideas to understand how the brain generates consciousness. And when we try to create machine consciousness, we have to solve two things. The first one is obviously we have to create consciousness. But in this creating consciousness aspect, we try to focus on functions of consciousness. So some philosophers consider consciousness is just an epiphenomenon, so it doesn't do anything, it doesn't have any causal role. Whereas we can also consider consciousness as a product of evolution, so there must be some functional advantage. So, but this is an open question, but today I want to present one idea, what the function of consciousness might be. And the second part is we have to be able to measure consciousness in any artificial system. And so, but the second part is measuring consciousness has to do with a problem called the hard problem of consciousness, which is there's no a priori reason to believe that certain physical interactions give rise to consciousness. So at least there's some sort of a conceptual gap what physical systems are and our phenomenal experience. So in the first part, I'll briefly propose the function of consciousness is to, how do I say? Let me skip a few slides. So this is the hypothesis I want to propose. So the function of consciousness is to generate sensory representations which are detached from the current input. And so if I read this, so agents with the ability to generate predictions of their own future and past sensory representations disconnected from the current sensory states have consciousness. It's a hypothesis, but once we formulate consciousness as such, we can explain many cognitive functions associated with consciousness. So of course, to do this, maybe let me go back a few slides. So maybe one insight into this hypothesis comes from the so-called V1 hypothesis. So it was proposed by Crick and Koch in 1995. And the idea is activities in the primary visual cortex V1 are not participating into consciousness. The reason is comes from the biological usefulness of conscious perception. So obviously, when you perceive something, it's useful because it gives you the best current interpretation of the input. But once you become aware of some sensory input, you can use it for many different purposes flexibly. So let's see. So, for example, there's a famous patient called DF who had the damage to her lateral occipital cortex. And then she can perceive shapes consciously. But if she's asked to post an envelope through an oriented slit, then she can actually use the information of the orientation of the slit. So in that sense, that information is somehow available to guide her action. But if she's asked to post the envelope, after 3 seconds, she saw the initial stimulus, then she couldn't do it. So if we need to act on something we internally generate, then suddenly we need awareness. So in that sense, this kind of something like imagination based on internal model seems very crucial for functional consciousness. And there's also something called Ramachandran's 3 laws of qualia. So these are properties of subjective experience proposed by a psychologist called Ramachandran. And the first property is irrevocability. When we perceive something like an apple, then we cannot change our mind, and we can override what we are perceiving. So in that sense, this representation of our consciousness needs to be insulated from top-down sort of override. Whereas the other 2 aspects of consciousness are related to non-reflexive behavior. So if there's a simple one-to-one mapping between the input and output, then it's a reflex. But when we, as I mentioned in the context of V1 hypothesis, when we become aware of something, we can use that information for many different things, including planning. And then that naturally also incorporates short-term memory. So hence I propose this idea. So the function of consciousness is to internally generate sensory representations when and which can be dissociated from the inputs. And so once we have that, for example, intention, which is closely related to the idea of consciousness, is very easy to implement. So when you have a forward model, so for example, I can imagine how I would feel if I were to reach out to a glass of water. I could internally generate a possible future sensory input from my fingertips and also from my peripheral vision. But then this can happen also at a more higher level, and then that could be planning or imagination. And then in the context of Ramachandran's 3 laws of qualia, once we have our behaviors are driven by the representations internally generated, then they can produce non-reflexive behavior and short-term memory. But actually, these things are really trivial in the context of AI, because you find many kinds of intrinsic motivations which are based on forward model. And also, one of my colleagues, Martin Bill, wrote a paper that tried to provide a unified framework of intrinsic motivations. And also, in neuroscience, there's a theory called free energy principle proposed by Carl Friston. And then there's an interesting concept called epistemic value, which could be also considered as a kind of intrinsic motivation. And also, once you have a good internal model or a forward model, you can use it for model-based reinforcement learning, reasoning, planning, and so on. So these are very, very common things. And then the question is, if you implement those things, can we get consciousness? And probably the answer is no. But I think I want to relate this kind of generative process to some aspects of the brain. So in the previous talk, we heard about how BAE works, so the basic idea is when you have an input, so you have this kind of initial sort of compression process, and then once you have some sort of latent representation, you can use that latent representation to generate images or any more sensory data. But in the brain, we find something very similar, which is this kind of hierarchical organization. So when you have an input, according to one theory called predictive coding hypothesis, the initial inputs are sent feed forward to higher sensory areas. But But eventually, so in that sense, this is a compression. But there's a lot of feedback processing or feedback connections in the brain that kind of predict what's coming next. So in that sense, this altogether works like an autoencoder. And so we can draw some analogy between this encoder-decoder perspective to the brain. So here, information generation I'm talking about corresponds to this kind of this decoding part. So whenever information is generated through decoding from a latent space, I would say, according to my hypothesis, consciousness is generated. And so, but in the case of the brain, this consciousness generating part corresponds to this feedback. So, but actually in neuroscience, there's a lot of evidence that shows we actually need feedback to consciously perceive something. So for example, in electrophysiology studies of primary visual cortex in monkeys, when a stimulus is presented, there's an initial spike, which then later there's an additional activation called delayed activity. And when monkey consciously reported the presence of a stimulus, then there's this delay activation. Whereas when the monkey failed to observe that stimulus, then you don't observe this. So this additional activation associated with consciousness has been connected to successful conscious perception. But nobody knows why we need this kind of recurrent processing for consciousness. But also more recent studies done in mice shows if you can, in mice, you can selectively suppress feedback signals. And then that also seems to eliminate subjective or some sort of like a report of sensation in mice. So it seems feedback connections play a really significant role in consciousness. But this hypothesis sort of explains why this is important, because the idea is what we are seeing is not actually just a simple data compression from the external world, but instead what we are seeing is the generated images. So we are always generating images. And actually, in the human psychology, there are many, many examples where feed-forward initial sweep can reach really high-level visual regions, but they don't evoke consciousness. But consciousness happens only after feedback activations go back to early sensory areas. Okay, but of course we can use these things to use these ideas to create conscious agents, but I want to show just one application. So for example, when we have a generative model of the future, including future action sequence and possible future sensory inputs, using something like an autoencoder. And then we can now use this generative model of the future to optimize behavior. So for example, for this kind of like very simple card pull task, we never trained this agent to move to the right or move to the left, but this one has learned how its future sequence might be generated. And so we just give it to a new task, such as moving sinusoidally to the right and to the left, but then it can generate many possible futures and then pick the one that goes to the desired state. So that's like a planning, but this is a really like a toy example. But once you have the good feed-forward model learned through experience, then the thing is we can optimize any statistical parameters that we want to optimize. But this is just a proof of concept. But for the sake of time, I just move to the second part, which is how to measure consciousness, because this is a really tricky issue. But so what I want to claim in this section is we need a theory of consciousness to make inferences about the presence of consciousness in AI. So for example, when we think about seasons in Australia, we maybe like, if it's like 500 years ago, it would have been like really difficult to test whether Australia is now in winter but we have a theory of seasons, right? So we explain seasons in terms of the tilt of the axis of the Earth, and then this theory can predict that the countries in the southern hemisphere have the opposite seasons. But now this is very easy to test. But we also use a lot of knowledge about physics to make inferences about what at the core of the Earth. So it seems like compared to consciousness, we seem to be able to actually reach the core of the Earth, but actually it's very difficult to actually go there and test. So a lot of times, even in science, observations are indirect, and we use theories to make inferences about what we cannot directly observe. And the same is true for exoplanets. So we understand the world only through the lens of theories. So what kind of theories do we need for consciousness? So one is, it has to be about intrinsic properties. So what I mean by that is, so your consciousness doesn't depend on my observation of your brain. So your experience needs to be explained in terms of the causal interactions happening in your brain. So that's the intrinsic perspective. And so, but other times neuroscientists and also maybe some AI researchers fail to see the importance of this because, for example, neuroscientists would present different kind of images and then look at the activations in the brain and see how they are corresponding to each other. But for neurons or for the units in latent space, all they can see is their relationship with other things. So there's no red neuron or green neuron, but the redness needs to come from the relationship of that neuron with respect to all other things. And another thing is axiomatic, but it's a complicated thing. But the idea is we need to start from some assumptions, which is also true for many scientific theories. And the theory also needs to make predictions. And it needs to be empirically tested. So maybe this is a good figure. So I want to introduce something called, integrated information theory. So according to this theory, it takes an intrinsic perspective of the system and then try to explain phenomenal consciousness in terms of information structure that's present inside the system. And I'm not. Yeah, so there's a lot of debate whether this is a good theory of consciousness or not. But at least the great thing about this theory is it takes an intrinsic perspective. So in principle, if you compute this value called phi, and in AI or in any other artificial systems, at least it gives us some measure of consciousness. But no other theory has that kind of property. But of course, it needs to be empirically tested. So the idea is this integrated information theory has a set of axioms, such as consciousness is informative and consciousness needs to be integrated information and so on. And so then they are all translated into mathematical formula, and then they can make predictions. So given this kind of system, this must have consciousness, or this value phi needs to be higher when someone is awake, but this needs to go down when someone is under anesthesia, for example. And then we compare whether this prediction is true or not, and then see whether this theory is correct. But this has the same structure as other theories in physics. So for example, quantum mechanics come with a set of axioms, and same is true for relativity theory and so on. But the important thing is predictions need to be compared against empirical observations, and then we can update the theory. So basically, we want to know whether some neural networks or some robots have consciousness by applying this kind of theory. And so right now, we have only integrated information theory, but we are also trying to create new versions of integrated information theory. But anyway, so what is integrated information? So just briefly, it's about, okay, so let's take a system like this. And so it could be a dynamical system, or it could be just non-dynamic. But this kind of system can be like written as a joint distribution. But then you split the system, making subparts independent from each other. And so this gives you a different probability distribution. So basically, KO divergence between them gives you how much information you lose by the cut. And in integrated information theory, you test all possible cuts and then try to find the cut that minimizes this value or this KO divergence. And then that's called phi. And there are already many different versions. And so the initial in IIT1, it's based on mutual information. And then there's an empirical version of phi, which is called stochastic interaction. But then Oizumi in my company developed two kinds of new empirical measures of phi. So there has been, but these are based on IIT 2.0, and then now the most current version is called IIT 3.0, and there will be another version coming called IIT 4.0. But we are working on IIT 1 and 2 because from IIT 3, computation gets even harder. Since I mentioned we have to find the cut that minimizes the loss of information. So when you have like two elements, you have like 2 to the 4 possible cuts. And so as the number of nodes increase, so basically the number of cuts you need to try increases exponentially on the order of 2 to the n. But recently we developed a method to speed up this computation. So now we can find this minimal information partition in a polynomial order. And then, okay, maybe for the sake of time, I'll skip this. But the point is, integrated information theory proposes that consciousness happens at the subset of the system where this value called phi is maximized. So it's a local maximum. So the idea is this structure called complex corresponds to consciousness. So in theory, like this could also move around dynamically. So then to test IIT, so to test IIT, we computed phi and the complex from like real monkey brain with 128 electrodes, and then we used like a bipolar. We combined like neighboring electrodes to make bipolar measurements, and then they actually tried to compute phi and the complex, and they compared that when the monkey is awake and when the monkey is under anesthesia. And so for example, like we can find like many complexes like this, and then weighted them by the amount of phi. Then we get some sort of a distribution of where consciousness is in the monkey. So then if you compare conscious versus unconscious, this information cluster or information core called the complex seems to cover this occipital, basically back of the brain when the monkey is conscious. This area corresponds to the visual cortex, but this is also still covered when the monkey's eyes were closed. And whereas complex starts being a little bit dispersed when monkey is under anesthesia and then loses this part. So it seems maybe there's some sort of qualitative difference in the way information is integrated between anesthesia and awake states. But this is still preliminary, and we are still developing our algorithms so that we can actually compute integrated information in real systems. And so right now we are working on animals, but in the next step we also want to analyze how information is integrated within artificial neural networks. Okay, so just to quickly summarize, so the point in the second part is, so it seems like consciousness is impossible to observe or measure from an extrinsic viewpoint, but it is common to make inferences about the presence of consciousness or other things in science indirectly, as long as we can extrapolate theories. So, for example, if we can maybe like something like IIT like 10.0 will become like so perfect, and then we are all convinced that it gives us a good measure of consciousness. Then we can start applying it to other things like maybe we can compute whether planets are conscious or any like very smart AI are conscious. So of course, we won't get direct answer to those questions, but establishing a good theory based on the kind of consciousness we are familiar with, which is like our consciousness and maybe possibly some other animals' consciousness, is an important step. And another thing is integrated information theory has been like heavily criticized because it's impossible to compute, but now we are developing a lot of algorithms to actually make it testable. And finally, we believe other people's consciousness are impossible to reach, but if we actually directly connect human brains with high bandwidth, we may be able to actually communicate our subjective experience. It sounds like science fiction, but actually there's actual twin sisters whose brains are congenitally connected to each other, and then they seem to be able to experience each other's qualia. So in that sense, maybe this property of privacy of consciousness is just due to our biological constraint, and maybe future technologies will make conscious experiences public. Okay, yeah, that's it. Thank you very much.
Okay, thank you very, very much. And here come the questions.
Oh.
Exactly. So, let's start with Simon Anderson, GoodAI. Hello, Simon. What would be the simple system satisfying your requirements for consciousness?
Well, I think bacteria may already have consciousness because they seem to be already doing a little bit like model-based inferences. So I'm a bit of a panpsychist. So even like really simple system, with AND gates and so on, may have minimal level of consciousness. So I believe consciousness is a continuum. So there's no simple threshold.
Dan Robitsky, futurism. Dan, where? Up there. Sorry. Gentleman on the balcony. Does AGI need to be conscious, or can it simply be convincing?
I think consciousness may happen like relatively simply. So in the first half, I emphasized the importance of generative models or information generation. And I think one way to create AGI may be to combine many internal models in a flexible manner. So that requires the presence of some generative models, and that, in that sense, as we try to create AGI, maybe like some of them may become conscious and we just don't notice it.
Which kind of like nicely bridges into Alex Yudakov's question. Alex, over there. And the iPad just moved it. Do you think that you need to develop consciousness for AGI separately, or can it emerge as a result of building complex enough intelligence?
Well, I think it's a latter. So I think probably consciousness, I think some people who are not interested in consciousness may end up creating consciousness. But my approach here is more about understanding consciousness, because I think there's something fundamentally missing in our understanding as a human society. And if we understand consciousness, there might be something useful from there. But I think it's probably quicker to create a very strong AI, even as noticing that we created consciousness.
Will you just say understanding consciousness as humans brings us to a question by Jan Musil from neuronium.info, over there. Could you elaborate on the limitations of neural activity measurements in explaining consciousness?
Oh, limitation of neural.
Yeah.
Well, I think the limitation is theory and concept. So, for example, with like a lot of neural networks, we are so familiar with the idea of latent representations. But that kind of thing doesn't really exist among neuroscientists. And also, if neuroscientists often talk about meta-representation, but that's again vague. But I get a lot of more concrete ideas or sort of a possible mechanistic implementation from AI. So I think neuroscientists should study AI and then go back to the brain and then try to see if similar mechanisms exist in the brain.
And this brings us nicely to our last question for this round from Jens Osolins from Cognizant over there. Do you think physical substrate is important for consciousness?
Oh, that's a very difficult question. Well, I tend to think yes. Probably simulation of consciousness is not conscious. I think, yeah, it's difficult to answer, in a short sentence. But I think consciousness is what information feels like, but then we have to define what it means to have information in this physical reality, and I think it's related to actual causal relationship. So, yeah, so we probably need to have very specific kind of causal relationship to generate conscious experience, but it's just a speculation.
Okay, let's thank the speaker again. Cool talk.